So today we are going to continue with our discussion about how to solve 3D frames, but we are also going to add something to it this time. We are going to add the idea of being able to find the stresses that are induced in little elements of material in the component parts of a frame like this. That's not necessarily trivial to do that. In order to get those stresses, we do need to do the static analysis of the frame first. And so that way we can get the reactions that will occur at the support where we are curious about the stresses that are induced in the part where we want to find those stresses. So in this case, back there at location A, that is where we're going to try to find the stress components that are experienced in the little element or the part that is fixed there at location A. We're given a little bit of information about the geometry of this setup. We're also given a few of the different kinds of connections, and we'll discuss those a little bit. We're also given what the cross-section is of the member that extends from A to B. So that cross-section is tubular shaped with a wall thickness of 60 thousandths and an outer diameter of 1 inch. And what we're supposed to do is find the stress components on the two patches that are shown that are labeled 1 and 2. I know they might be kind of hard to see right there, but all the way back at the wall, essentially, we're going to try to figure out the stresses that are induced in those little patches of material. All right, what should we do first? Freebody diagram. You are on the right wavelength, okay? I guess that'd be a little bit more of a physics kind of a concern, but anyway, so what we want to do is a free body diagram of what? All right. So one of the things that we look for when we're doing a problem like this is if it's possible for us to set up equations that can be solved kind of sequentially rather than having to be solved simultaneously. That's typically helpful because it allows us to get intermediate answers along the way, and it's a little bit less computation that we have to do to get that set up. If you're going to pick one of these members where it looks like you might have a smaller number of unknowns, where would you expect that might be? Okay, the linear bearing assembly. Specifically, like if you actually look at this sort of T-shaped member that it goes from where the 100 pounds is being applied up to C and then across from D to E. If you look at that one, there are two members. There's one at EG and there's another one at DH, right? What kind of members are those? Okay, good job. A lot of you are saying those are two force members. How do you know that those are two force members? Okay, they have ball joints at the ends, and how does a ball joint behave? Okay, ball joint's kind of like your hip joint that you have. It's basically a ball inside of a socket, and what it does is it constrains translation for one member relative to the other. It constrains that, but what does it not constrain? Rotation. It's allowed to rotate any direction, one piece relative to the other. Okay. What that translates into on a free body diagram is that there are no applied moments, right? All you've got is forces, no applied moments, all right? And if there's no applied moments, and if there are only two attachment points and no external loads applied on it anywhere, then those meet all the criteria for it to be a two-force member, all right? So you might remember that all the way back to your first statics class. We looked at some criteria for knowing whether or not something was a two-force member. So basically the rules back then were if you had a member that was connected only at its ends with frictionless pins and no external forces applied to it, then you could assume that the member was going to be a two-force member. I'm basically extending that out to 3 dimensions for these pieces, all right? They are connected only at their ends with frictionless ball joints, okay, and no external loads applied anywhere else. So those are two force members. Since they are two force members, how does that make them special with respect to finding maybe some equations or, some values once we get ready to do the static analysis. Right, there's one unknown that's going to be associated with the force carried in either one of those members. You can purely boil it down to a certain amount of either tension force or compressive force, but that's just one unknown. All right, because you already know the line of action along which the force will be applied for those two members, DH and EG. And because you already know that line of action, then typically what is done is you don't usually even draw free body diagrams of two force members, right? You just draw the members that those members are applied to, right? And it only adds one unknown per location where there's a two force member applied, okay? So, having said all of that, does that give us a little bit more of a hint as to where we might be best off starting with this problem? Okay, where should we start? What free body diagram should we maybe draw? All right. Maybe that T-shaped piece, right? Going from the 100-pound load through this linear bearing and spreading out right there. That might be the best free body diagram for us to draw first. And I'm just going to do that kind of beside it right down here. Okay. So there's a sketch of what the body looks like. It's very simplified, but it's enough for what we are trying to show. Okay. What sorts of forces act on this part? Okay. We definitely have a 100-pound externally applied force being applied along this axis. Okay, so that's easy for us to just copy that over. Okay? What else? How do I model the forces that are being applied by the two force members that I spent a second talking about just now? Okay, so I could maybe apply a force that I call maybe TDH, right? And that force that I apply here, TDH, do I know anything more about the direction of that force? Okay, what else? Okay, maybe the best way to say it is that I might know the slope, right? If I kind of think about drawing a little triangle right here, and the fact that it's given here with a little triangle, I know that for a run in the negative x direction of 1, there's a rise in the z direction of 2. Do you agree with that? So this would be 2, and this, whoops, excuse me, that's 1. 1, and that's 2. Okay, and that's helpful to us because it helps us know how much of that force points in the x direction versus how much points in the z direction. All right, what else? Okay, there's a force here, EG. So I may as well call that something like TEG. Okay, it would also be okay if you wanted to. You could call it, because that force is entirely in the z direction, you could maybe call it something like EZ. Okay, totally up to you what you name your variables. I mean, that's up to you. Although I do recommend you choose things that are wise so that you know what you're talking about. So anyway, let's call it TEG. All right. What else on my free body diagram? All right, I'm going to have some reactions at point B. Okay, so let me put that right here. I'll kind of draw point B. What kind of reactions do I expect to happen for a linear bearing like this? Okay, sometimes the best way for us to deal with this is to look at what direction does it allow movement. Because any direction it allows movement, it will not have a reaction. Any direction it does not allow movement, it will have a reaction. Okay, so what directions does it allow movement? Along the x direction linearly. And what else do you think? Okay, rotation around the x-axis, right? So it can slide along the x-axis, and it will be free to rotate around the x-axis. So those are the directions we will not have reactions. The other directions where it constrains movement, that is where we will potentially have reactions. So that would be what directions? Okay. Someone says a z direction of reaction. All right. So let me just call that bz. Okay, and someone I think said a y direction of reaction. So let me call that by. What else? Okay, there could be a constraint against rotation around the y-axis. And without telling you why, I'm going to choose this direction to be positive to describe that reaction moment. Okay, and what did we call this? You know, what was our naming scheme we did last time? Maybe M, B about the y. All right, so that's a moment applied at B around the y-axis. And what else? Okay. Z direction, right? So there's another one that happens here around the Z. So let me show that one like this. Okay. And I can choose whichever direction I want to for these two components. In other words, I can choose either negative according to the right-hand rule or positive according to the right-hand rule at this point for those moments. Why is that? Why can I choose whichever way I want for this diagram? Because I haven't drawn another one yet, right? Because I don't have to match relative to an earlier free body diagram that I've already drawn. This is my first one, so I get to kind of choose what direction I show those. I may be wrong, right? They may not actually go that direction, but I get to choose, and if they're wrong, then the answer that I come out with after I've done my solution will let me know whether or not those directions were wrong. Does that make sense? If they come up with negative answers, it tells me that the direction I assumed that those moments acted was incorrect, if it turns out to be negative. All right? Anything else? Does that take care of location B? What do you say? Does that seem about it for location B? Yeah, that looks like it'd be about it. Do I have any other forces that I haven't accounted for yet? One of the answers I might get would be, what about self-weight? What was the guideline we said last time? Okay. If it says to account for it, then account for it. Otherwise, as far as the problems I give you, you can kind of ignore it. Okay. Again, that may not be a wise rule always in real life, but that's what our typical approach is going to be in here. Okay, so what else? What else do I need on my free body diagram? Dimensions. All right, so I should put on a dimension, let's say over here, of 2 feet, saying that that's how far it is from this location over there. It's 3 feet right here. Okay, and then it's 4 feet going from this location over here back to point B. All right. And one of the other things I typically like to do is also label all of my locations, right? So this was location B, this is C, this is D, and this is E. All right. So far, so good. Before I draw another free body diagram, what do you think a good strategy might be for the solution of this problem? See if there's anything I can find out of this one, right? That might not be a bad strategy. So do you see a direction I may sort of start with? Okay, someone says X, I heard, right? So with equilibrium equations down here, okay, I can start with a sum of forces in the x direction, which, by the way, I didn't actually copy my, my directions on here either, did I? So let me say that's x, and for the purposes of this diagram, let's say that this is z and this is y, just to be clear here. Okay? So in the x direction, okay, what kind of forces do I have there? Negative 100 pounds. And what else? Okay, TDH, I hear some people saying, but not all of TDH points in the x direction. Only a portion of it points in, only one component of TDH points in the x direction. So I need to do something to pick off just the x component. Okay, and so when I do that, I say minus TDH, okay, because it's pointing in that negative direction. But instead of taking all of it, I multiplied it by what? Okay, 1 over the square root of 1 squared plus 2 squared. Okay, and you've seen that technique used before, I hope, where you use the slope indicator and the idea that there's a triangle created right there, and based on similar triangles, you can use that factor to pick off just the x component. So I took the piece that points in the direction I want, and then divide by the length of the hypotenuse, if you will, of that little slope indicator. Okay? And it's basically similar triangles is the basic theory behind why that's okay. Any other forces along the x direction? I don't see any. So once I calculate all of this, it ends up giving me that TDH is equal to negative 223.6 pounds. What does that negative mean? Okay. It means that the direction I showed the force is actually opposite of what it really does. All right. And especially with respect to two force members, if you define them like I did here, and I even named it accordingly where I used T to kind of indicate tension, the negative means what? It's got a compressive force in it, not a tension force. Okay? So specifically for two force members, that sign can kind of mean something if you've defined all your two force members so that you assumed tension was positive for all of them. Okay? All right, what's next? Is there anything else we can do with this setup? Okay. In the y direction, I hear someone say, okay? So y direction is kind of a special case. Why is that? Okay, I have by. Do I have any other forces in the y direction? Nope. Well, that was easy. Okay. Before I leave this point, though, what could I have done to this given problem if I wanted there to be a non-zero by? I got to change one small little thing, and it would have changed that outcome. Like what? Actually, there's a bunch of things I could have changed. Like the 100-pound force, I could have shown something that wasn't entirely in the x. Right? If I gave something there where that 100-pound force also had a y component, right? It wasn't directed perfectly along the x, then I would have had to react that with something. What else could I have done? Yeah, y component with either one of my two force members, that would have made it to where we would have had to have a reaction there at B in order to react against those forces that would have been generated in any two force member that had a y component. Okay, so just pointing out here that the reason that turns out to be 0 is due to the specific geometry of this problem, nothing bigger than that. Okay? What next, do you think? Okay? So someone suggests a moment about why. Let's see if we, how many things do we either know or not know with respect to that? Okay, we don't know TEG, and we don't know, okay, you're saying around the Y, right? So we don't know TEG and we don't know MBY. So there's two things we don't know there. So we try to keep looking and see if there's a different one we might be able to use that we can get just one thing we don't know. Okay. If I sum moments about X, someone suggests, that one's a little bit different because around the X-axis, I will not have a reaction moment at that linear bearing. So that eliminates one of the unknowns that I would have had around the Y that I took care of, or that I just discussed a second ago with respect to a sum around the Y-axis. So that one looks preferable to me to take a sum of moments around the X-axis, and again, kind of using the, I've used a little bit of notation like this before where I indicate this is an X-axis passing through point B. All right. So what kind of effects do I have rotationally around that axis? Okay. Maybe the easiest one is TEG. Okay, because keep in mind, what I'm trying to do is work around this axis BC. TEG, what kind of an effect does it have? Positive, right? It's going to tend to rotate such that if you stuck your thumb in the positive x-axis, your fingers would rotate the same direction as the effect of TEG, right? So that means, according to the right-hand rule, TEG is going to have a positive effect around that axis BC. So I'll take TEG multiplied by what? 2 feet. Okay. What other effects do I have rotationally around this axis BC, this x-axis? Okay. I heard someone say the vertical component of force TDH. Okay, and that's really good, right? The reason we only look at the vertical component is that you basically imagine this force being split into a component here and a component here, right? The component that goes along the x can't create a moment around the x because it's parallel with the x, so it won't create moments around the x. So only the one that is perpendicular, right, that z component essentially of TDH will create a rotational effect around the x-axis, all right? So, what do I do there? Is it positive or negative? Negative if you just look at the direction of the arrow, which is what you should do. You just look at the direction of the arrow and you say that upward force that's applied at D will tend to rotate this thing such that if you stuck your thumb of your right hand in the negative x direction, your fingers would roll the direction that that effect would happen, right? So, I say minus TDH, okay, I would need to multiply by whatever it took to get just the vertical component. What do I need to multiply by there to get that? Okay, 2 over the square root of the square root of 1 squared plus 2 squared. Okay, so far all I've done is I've picked off the vertical component of TDH. What else do I need to have here? The distance, so 3 feet. All right. Any other effects that I haven't accounted for that would create rotational, influence around axis X? Okay. BZ will not because it passes through that axis, right? BY will not, it also passes through that axis. MBZ is not around the correct axis, right? So it won't. MBY won't. And the 100-pound force is parallel with the direction I'm summing these moments around, so it won't. So I've accounted for everything now that I need to in this direction. Okay? And not only that, but I have this negative 223.6 pounds that I can plug in right here. All right? And when I do that, I should be able to solve this thing for TEG. All right, and TEG ends up being negative 300 pounds. Y'all are doing great so far. What now? Okay. Someone says we can go back to our other moments. All right, and I think I agree with that statement. Which one do you want to go to next? Okay. If I wanted to go to the one someone suggested a minute ago and some moments around the y-axis passing through B, what influences would I have around that axis? Okay. Minus MBY is an obvious one, right? That's definitely just a concentrated moment that's applied around that axis that I'm mentioning. But what else? Okay. TEG, would TEG contribute positively or negatively according to the direction that TEG is drawn on the picture? Positive. Okay. So TEG multiplied by what? 4 feet. Okay. That's the distance perpendicularly from the line of action of TEG to this axis y. That's how far that is, right? So that's why I got 4 feet there. What else? Okay. I also need to account for the vertical component of TDH. Okay. What effect is that going to have rotationally around y? Okay, also positive. So I say plus TDH, but just the vertical component. So I multiply by 2 over square root of 1 squared plus 2 squared. And multiply that by what length? Also 4 feet. All right. Any other forces that I need to account for this sum of moments? That should take care of it, okay? And once I've done this, I can, again, I can plug in TDH, right? That goes right there. And then I also know TEG. So when I plug those in, I only have one thing I don't know, and that's MBY. So when I solve it, MBY just becomes negative 2,000 foot-pounds. All right. Where to now? Okay. Someone says we could sum forces or moments in the Z. You know, I agree to both of those. Which one do you want to do first? Forces, okay. So let's sum forces in the Z. And there I've got BZ plus TEG plus what? Okay, TDH, but just the Z component of TDH, right? So I say plus TDH times 2 over the square root of 1 squared plus 2 squared. Okay, any other forces in the Z direction? So that sums to 0, and TEG and TDH are already known. And when I plug those values in for those two, TEG and TDH, I can solve for BZ. Okay. BZ winds up being positive 500 pounds. All right. This is good so far. We've done 5 of our 6 possible equations that we can write here. What's next? Okay, summing moments around the Z. Okay, so summing moments around the Z for an axis passing through B. Okay, again, a lot of times the first thing I will include is the concentrated moment applied at that particular location. A lot of times I'll do that first if it exists. So MBZ. MBZ, does it go in the positive or negative direction relative to the positive direction I have identified for Z? Negative, okay? Y'all are good at this. Negative MBZ. Okay. What else? Okay, someone says the x component of TDH. I agree with that. So if we look at just the x component of TDH, does that create a positive or negative rotational tendency around Z? Okay, negative, I hear several of you saying. That's right, because you're basically pulling to the negative x at this location that's in this negative y location. That'll tend to rotate it in that negative Z direction. So these things are hard to describe other than just say, try to use the right-hand rule and figure that out, right? So, so I need to do negative TDH and just pick off the x component. And then multiply by what? 3 feet. All right, so that would take care of the influence of TDH. Do I need to think about the Z component of TDH? No, why not? It's parallel, right? It's parallel with the direction I'm trying to find this moment, so it's not going to create a rotational influence that way. And I think that actually takes care of everything. 100-pound force, lines of action goes right through the point, right, where that axis exists, as does BY, as does BZ. TEG is entirely in the Z, so this takes care of everything for this moment equation. And if I punch in the value that I know for TDH, this thing will solve to a MBZ of 300 foot-pounds. All right, yeah.
So before you did any of these equations, if you started with a sum of the moments about the y-axis going through C, would you have to take into account MBY?
Okay, so the question was, before I did any of these, if I was to take a sum of moments around a y-axis passing through C, and then what was your other question? Would I have to account for MBY? And the answer is yes. Any concentrated moment that you have around a particular axis, it doesn't matter what axis that you pick, like what point that axis goes through, you have to include it in the sum around that particular direction, right? So they sort of exist, you just add them in as a term regardless of where it's located, where that axis is located, as long as it's a parallel axis, right? May have not done a great job of explaining that, but the answer to your question is yes. All right, so that actually takes care of all of those reactions. How do those help us?
Now we know
Okay? He says, now we know what's going on at the linear bearing, but how does that help us? Not yet. It doesn't help us at all yet, but what it does is it gets us one step closer to figuring out the reactions that are occurring at A, which is important to us. Okay? So to do that, what's maybe our best move at this point? Draw a free body diagram. You guys are definitely with it here. Okay? Let me do this. I'm going to draw a little free body diagram like this and show the little kind of T head on the thing like that. Okay? And the reason I'm drawing it here is so we can see everything that we need to see. All right? This is point A. This is point B. All right, I'll just stick it somewhere. I may have to move it when I start looking at how I want to draw my reactions there, but that's point A and point B. What kind of reactions should I show at B? The opposite of what I drew a second ago, right? So if I have an MBY shown the direction that I showed it there, well, actually, let me start with BY, right? Whatever BY I had originally, I should show it reversed, right? All right, so then what? Someone says MBY, right? Opposite the direction that I showed it. Okay, so that would be this way. What else? BZ. Okay, so BZ can be shown that way. And what else? MBZ. Whoop. This direction, correct? All right, what else? What else acts on this member? Okay, and someone says A, what reactions happen at A? Okay, all 6, all right? If you look at this is called a fully fixed connection here at A. It means all your possible reactions exist there. It's not allowed to move in any direction. Member AB is not allowed to move in any direction relative to this sort of fixed location that I've identified there at A. Okay, so what does that mean? Okay, I can just draw them on there, right? I can go for some in the Z. All right, so this would be like AZ. There would be an MAZ. Okay, there's also maybe an AX. There could also be an MAX. Okay. Also, there could be a force in this direction called AY. All right. And maybe a moment in that direction. MAY. All right. Let me kind of finish this up just a little bit by putting on some axes. Okay, so this is the Y direction. This is the X direction. And that's the Z direction. What else should I put on here? A dimension, right? And based on the picture that we showed originally, it looks like it should be 3 feet from where the rod comes out of the wall there to point B. So I'll put that on here as 3 feet. All right, so that's a nice little free body diagram that we should be able to use to figure out what we want to know. So I'm going to slide down here and use it down here. Yeah. If you have not, so the question was, when you're making your initial assumption about the direction of the moments, or forces for that matter, do you just throw something up there is the question. And the answer to that is, it's got a couple of folds to it. So first of all, the answer to that is yes, as long as you haven't already drawn something on another free body diagram, right? So, you know, if you're talking about a particular reaction between two parts and you've already expressed that reaction on one free body diagram, you should be consistent and draw it equal and opposite on the other free body diagram. But if you haven't identified, you know, a particular reaction yet, then you are free to assume one direction or the other. It doesn't matter which direction you assume. And when you actually get around to solving, then the signs of your solution will tell you whether or not you were correct. Sometimes what happens is, as people get more and more comfortable with these, they'll be able to visualize what direction should end up being positive, and they'll end up being able to guess more of them right up front, which in some cases helps a little bit with clarity. But I actually like the idea of developing the discipline of not caring and just, I don't know and I can't tell just by looking at it. That's okay. I'll just stick one on there and then I'll rely on my my algebra to tell me whether or not that direction was correct.
That's what I was wondering, because I feel like I spend a lot of time trying to figure out what's happening.
Right. Don't waste time on that. Give it your best guess, and if you haven't already used it in another location, that's good enough. And you go ahead and you just have to be careful with all of the signs in your solution. And if you do that, then the outcome, the sign of the outcome will actually let you know whether or not you chose correctly. Good question. All right, so what should we do now? Okay. Well, one of these things is actually real easy, right? By was 0. So it's like that one's not even there. Okay? And if that one's not there, then what's AY? Yay! Okay, we've got our first one. Okay, what about our other reactions? Okay, let's kind of get them in there. What's MBY? MBY was negative 2,000 foot-pounds. Okay. Why don't I go ahead and just do that equation real quick. Sum of moments, okay, around the y-axis, passing through A and B, but I'll just say A. Okay, for that I have what? It would be positive according to the direction my arrow is shown, right? But the value itself was negative. Okay, so I should say that this ends up being negative 2,000 foot-pounds due to that moment applied at B. Anything else that creates moments around this axis? MAY. Okay, so what does this tell me about MAY? Positive 2,000 foot-pounds. Okay. What do you want to do next? Okay, someone says forces in the X. Okay, sounds good. I have AX. Anything else? No, okay, nothing else in the X direction. Okay, so that one also ends up being pretty easy. Just for saving space, let me actually slide this one up here. All right, what else? Okay, summing forces in the Z. For this, I have AZ. And what else? Minus BZ equals 0. And so since BZ was positive 500 pounds, if we put that in down here, we solve for AZ is also going to be 500 pounds positive. All right, now what? Okay, we can go to, someone says maybe sum of moments around the x-axis. Okay. And we'll take that x-axis passing through A. Okay. So there I've got an MAX, right? That's that moment applied around that x-axis. What else? Okay. Anything else that would create a moment around that x-axis? All right, BZ. Okay. So BZ, the direction that it's shown, would create a negative moment around the x-axis, right? And the value of that moment would be 500 pounds times 3 feet. And this would sum to 0. Okay, so from that equation, MAX ends up being 1,500 foot-pounds. All right. We only have one left, right? What is it? Summing moments around the z-axis. Again, we'll say that is a z-axis passing through A. For that, I have MAZ. And what else? Okay. Plus MBZ. Anything else? Okay, that's it. But remember MBZ, okay, up here, MBZ was 300 foot-pounds. So what's MAZ? MAZ is going to just be equal to negative 300 foot-pounds. All right. So far, so good, right? Have we answered anything we were supposed to answer? Okay. We're supposed to be finding the stress components at these two patches. And we're, what, 40 minutes in now or something like that? That's okay, though, because we've made good progress, and what we have found as far as the reactions that are happening there at A are important to us in order to find these stress components. So what I want to do here is actually do a little sketch, zooming in really closely where this rod comes out of the wall. Okay, so like really big. Okay. And I'll tell you what, I'm going to kind of show it like this and indicate that, you know, I'm not going to show all that length in between one end of this rod and the other. Right here, this is point B, right? And out here, this was point A. All right, so let's look at these reactions at A and make sure we have those kind of figured out correctly. So, AZ, I have 500 pounds. Right? And the two patches that I want us to think about are a patch that exists right here and another patch that exists over here. Okay? This is such that the two patches sort of are aligned with particular directions, right? So this patch down here is going to be aligned such that this is the Y direction and this is the Z direction. Okay? This patch up here is going to be aligned so that this is the Y direction. And what's the X direction? So does this make sense? So the reason I'm drawing it real big is I want us to think about how do these forces and reactions just generally, how are those going to affect the stresses in these patches. All right, what other kind of reactions do I have at A? I started with the 500 pounds. What else do I have? Okay, MAX, all right, that would be a moment around the x-axis, okay, and that would be 1,500 foot-pounds. Okay, so did I have an X? I don't have an X force, right? So all I have here is just this MAX of 1,500 foot-pounds like this. Okay. MAZ, I have negative 300 foot-pounds. So positive, according to the right-hand rule, would have been kind of around this way. But because we have this negative, I'm not going to show it that way. I'm going to show it the other way. And kind of do that little flipperoo right there and say this is 300 foot-pounds. Okay. What else do I have there? Okay, MAY, right? MAY, you can kind of think of that as being the wall back here. And that wall is going to react a positive moment of 2,000 foot-pounds like this. Okay, and one of the reasons I show all this stuff is I want to show you this idea that all of these reactions that I just showed you at A, we're presuming that those are just ever so slightly toward the wall relative to where the patches are. Okay, so they're like behind the patches. So the patches represent material that are between all of these reactions that I just showed and what are causing those reactions. Right? What's causing the reactions are all these forces that existed out here on the end of this rod, right? For instance, there was a 500-pound force like this, right? You agree with that? What else did we have? Okay. What caused the MAZ was an MBZ, right? So there was, this 300-pound acting this way. There must have been a 300 foot-pound acting this way. Right? So That's what's causing this. And I'm trying to give you a good picture of that these patches exist between point B and point A, and that helps us orient how we're going to actually apply each of these loads correctly to those patches. Okay? What else, for instance? I have my 200 foot-pound reaction that happens around the Y, or not 200, 2,000 foot-pound reaction happening around the Y over there. What does that mean over here? Okay. Must mean I have a reaction or an applied moment like this. Okay, and we can actually look at our original stuff here and see that that must be correct. I had negative 2,000 shown in the positive Y, right? So that's the same as having just a negative 2,000 foot-pounds applied there like that. All right, let's see. Is there anything else I need to think about there? Oh, MAX, at 1,500 foot-pounds, where did that come from? Okay, it came from my 500-pound force applied at 3 feet away from where the rod came out of the wall. All right, that sets up a whole bunch of, good stuff, I think, in terms of being able to understand how these stresses get induced in the patches. What do you want to do next? How about we draw the patches? Okay. I'm going to kind of draw them such that they're relatively aligned with the direction that I'm showing them right now. So let's see. Patch 1 was up here, right? This was patch 1, and this was patch 2. So let me just show patch 1 right here. Okay. I'm going to show it so that this is my X direction, and this is my Y direction. And what we need to do here is start looking at the different effects that cause stress, right? So like what? Will I have a flexural effect in patch 1? All right, that's my first patch. Okay. If I did have a flexural effect in patch 1, what would the neutral axis be for patch 1? What would the neutral axis be for that flexural effect? Okay. It would be the x-axis, right? That would be the neutral axis. And then what moment effect would actually create the flexural stress in patch 1? Okay. Not the 2,000. 2,000 is a twisting action along the long axis of this member, right? The 1,500 foot-pounds would be the bending moment that's experienced at the wall that would create stress in patch 1, okay? And that 1,500, I mean, what you see there is there's a 500-pound force downward out on the end of the rod, and that's reacted by this 1,500 foot-pound concentrated moment at the wall. What effect is that going to have on patch 1? Is it going to make it try to stretch longer in the Y or to compress in the Y? Stretch longer, right? And so I'm going to draw that on here like this and basically say this is my flexural component, okay? And what would that value be? How would I calculate that value? Okay. Someone says there should be an equation in the back of the book. It also should be an equation that's in your brain, okay? Because there weren't that many of them for you to learn from mechanics and materials, right? There's two really big ones that have to do with stress. One of them has to do with torsional stress, and one of them has to do with flexural stress. We're talking about what kind here? Flexural stress. And what was our equation we typically used for that? MC over I, right? Where M is the bending moment, C is the maximum distance from the neutral axis to the outer fibers, and I is what? Second moment of area, right? For the cross section, yeah.
Could you kind of walk me through what's happening to cause forces pulling it apart? We're talking about 1,500.
Okay.
Right there.
So what's happening here? Someone says, I'm still a little bit confused as to what's causing this stress, okay? So we'll walk through it again. Here's what's going on. Let me kind of draw it a little bit more simply, right? I'm going to draw it so that basically here's the rod, and here was the rod how it started out. Agree? Something like this. And one of the forces we have on that rod is a 500-pound force downward here. What's that going to do to the deflection of the rod? Is it going to do that? If I really exaggerate it? Okay. What's happening to the material on the top of the rod? It stretches, okay? So that's what's going on, and that's why we end up with this tensile stress in patch 1, is patch 1 represents a portion of the rod that's going to have to stretch if this rod is going to start deflecting downward under that 500-pound load. Okay? But the moment that actually allows us to calculate it is the 1,500 foot-pound moment that has to be reacted there. That represents the bending moment that exists back there at the wall.
Okay. But it's caused by that 500.
And it's caused by the 500-pound force out on the tip.
I was trying to focus at where that moment was occurring at the axis and not thinking of the force actually at the end.
Yeah.
That makes sense.
Did you have a question?
Follow up on what he said. So we're looking at how it causes on the patch and show us we're looking at not reactions, but what causes the reaction.
So the question he asked is, whenever we are looking at the stress in the patch, we shouldn't be looking at the reactions. We should look at what causes the reactions. The answer is, you should kind of look at both, right? You get to the point where all you have to do is look at the reactions, and you can quickly interpret them for that means there's going to be a tensile stress, or that's going to, whatever. You're going to be able to interpret them quickly. For right now, though, since this is probably relatively new, y'all haven't probably spent a ton of time thinking about this just yet, what's helpful is to understand that there is a support and there is a load, and you're looking at material that's between the support and the load. And you want to look at what's happening with that material that's between the support and the load. So where I have my 500-pound applied out on the tip, and I have my 1,500-pound foot-pound that is reacting against that, patch 1 exists between those two locations, and patch 1 is stretching, right? And so that's, I wouldn't say it's one or the other. It's a complete understanding is that you have a force that's being applied and a moment that's being reacted, and then patch 1 exists between those two locations. Okay, and so if I'm going to calculate this and use MC over I, my moment is going to be 1,500 foot-pounds. Typically, feet aren't necessarily our best unit to be using in these stress type of equations. So what do you think I might want to do with my feet? Maybe get rid of them, apply a 12-inch per foot conversion factor there. What about C? Okay. How far is it from the neutral axis, which I showed right here, right? How far is it from that neutral axis to the patch that I'm looking at the stress in? Okay. It'll be the radius of that rod. Some of you may not remember what that was off the top of your head. Here's what the cross section was. 1 inch outside diameter with a 60 thousandths inch wall. Okay. That'll be important to us for another reason later. All right, so that means that we have 1 inch over 2 for that distance from the neutral axis to the outer fibers of the material carrying the stress. Now what about I? Okay, We covered this, I believe, last time, but when you're finding the moment of inertia, this is called sometimes, or the second moment of area, the formula for that is pi over 64 times the diameter to the fourth. Okay? But we actually don't have a solid rod. What shape is our rod? Okay? The rod we're dealing with is hollow. So how do I deal with that? Okay. 1 inch to the fourth minus 1 inch minus 2 times 60 thousandths. Okay. To the fourth. And if you actually punch these values in, the stress ends up being, make sure here, all right, yep, ends up being 458 KSI. Now let me ask you this, is that a lot? Kind of a lot, okay? This is so much that it's very hard for us to imagine that we have a steel that's that strong. So at this point, what would we expect may happen for a member like this? It'll at least, flex permanently, deflect permanently, permanent deformation, or it could actually completely fracture it. However, it's not uncommon for us to continue pressing on and just figure out, let's assume we don't have any strength problems with this material. Let's just figure out what the stresses would be in it. All right? So that's what we'll do for now. But understand that this is the kind of thing that if you were to actually say, oh yeah, that'll carry that much stress, no it won't. You don't have a material like that. Okay? So good to at least have that in mind. What do you think might be next? Okay? We could try to figure out whether or not there's any stress in the x direction, all right? Although that's not really the one I would look at next. The reason why is, in order for there to be a stretch in the x direction, we would actually need to see this body probably increasing in diameter, right? So it would create a stress maybe in that x direction if we had like an internal pressure inside of this pipe. That would create a stress in that direction. But none of the loads that we have shown right here would create a stress in the x direction, at least not a normal stress in the x direction. What do you think I might be driving at for our next stress that would be important to us? Okay, someone says shear. Shear caused by? Shear caused by torque, right? Torsion. And what would that effect be that's causing torsion? The 2,000 foot-pound moment around the long axis of this part. So let's go back and remember what's the formula we typically use for shearing stress due to torsion. Okay, TC over J, I heard someone say. Okay, so that's what we're going for. Stress is equal to TC over J. Okay. Let me ask this question before we go too far on this point. What direction, if I was to draw this shearing stress that's caused in patch 1 due to this, this torsion effect, what direction should I draw that on this patch? Okay. All right, what you can think here is with this 2,000 foot-pound torque applied in kind of the negative y direction on the front end, and then a 2,000 foot-pound torque in the positive direction on the back end, what I would guess would happen there is that a line that was maybe drawn down the length of this part due to this torque that's being applied, what would happen to that line? Would that line start to maybe veer off and maybe curve this way? Okay. So let's think to ourselves, if that line starts doing that, what shape would this element, element number 1, what shape would it start to be instead of like square shaped? Okay, it might go to more of a rhombus or a parallelogram type of a shape. And what direction would that go? Okay, it looks to me like it would go like this. Okay, does that kind of make sense? All right, that would be kind of the new shape. Well, what causes it to do that is a shearing stress that's applied basically like this, right? It's a shearing stress that pushes this way on that side and this way on this side. And you can see there, that is the direction that you would expect the 2,000 foot-pound torque on the front end. You'd expect that to sort of push this side of this square that way, whereas the 2,000 foot-pound on the back end, you'd expect that would push this square this way, right? So it's all consistent with what you'd expect that element of material to experience based on this torsion. One of the things I'm going to add here, because we don't typically leave just these forces, you know, kind of these shearing forces or stresses shown like this, those are balanced with other ones that would be along this side and this side. Otherwise, the little square of material would actually start to rotate. Okay, so a complete state of shear involves us having you know, all of those shearing stresses shown around the perimeter. And I'm just going to name this maybe tau due to torsion, like tau subtorsion. Okay, and that's what I'm finding down here is this tau due to torsion. All right, so what should I plug in for this expression? We've talked about it a lot so far for torque, right? So that's just going to be the 2,000 foot-pounds. Now, just like for the question of flexure, typically feet aren't really our friend in terms of these because we typically want to get them down into something like PSI, pounds per square inch, right? And so often what we want to do once we see that unit of feet there is to get rid of it by applying a 12-inch per foot factor like this. Then what's C? Okay. Yeah, C is the radius from the center up to where this patch is located. Okay, that distance right there is that factor of C. And that radius, just like we had in the first case, is just going to be 1 inch over 2. Because 1 inch was the diameter of this member. All right, how about J? Okay, similar format to what we had for I. Only difference is the formula for J, which is the polar second moment of area as opposed to just the second moment of area. It has a factor of 32 in the denominator instead of 64. Other than that, it's exactly the same. Okay, so pi over 32 times 1 inch to the 4th minus, and then here we're finding the diameter to the inside wall of this tubular shaped member, and to get that I take 1 inch minus 2 times 60 thousandths of an inch, all that to the 4th. All right. So once we punch those values into a calculator, this tau due to torsion just becomes 305.3 KSI. Okay, and so I'll put that up here. All right, so those are some components of stress that this little patch of material would experience due to the loading that we identified at the beginning of this problem. Let me ask you this, are there any other components of stress that I need to account for on this patch? Okay, the answer might be yes, might be no, all right. Okay, someone says no. Someone's bold enough to make a guess, right? And you should be rewarded because it is no, right? There are no other components of stress that we need to consider for this patch of material. Let me ask you this before we leave the point, though. Is there anything we could have done to this member so that there would have been another component of stress that we should have considered? Okay, I think maybe what's being suggested here is we could have had an axial component of stress. All right, if we go up here a little ways, you might remember that due to how the thing was loaded, By wound up being 0. All right, it would have been really easy for us to change it up a little bit and By not be equal to 0. Right? If By was not equal to 0, what would happen to the rest of the question here? If By was not 0, then we would have a force that would act along the axis of this piece. And then what would we have to do to find the stress that would be caused by that axial force? Divided by the area. It would just be a straight F over A type of a calculation that would happen there for axial stress. Once we found that F over A value, how would it combine with everything else that I did down here? Okay, the suggestion is, could it add to the flexural stress? And that's exactly right, okay, because both of those are going to put stress in that positive y direction, or I guess the axial could be in either direction depending on the conditions that we added there, but they would both be along that y direction, and so they would have to add together, okay? So figured I'd talk through that since we didn't have that component, but generally we could have that component. Yeah? Okay, the question that was just asked is what kind of loading here could cause a stress in the x direction? There aren't that many different kinds of loading that could cause a stress for a body like this in the x direction, but there are some. So the big one to note is that if this was a pipe that was carrying internal pressure, okay, that would actually cause two different things. It would actually add another component of axial stress. You might remember when we studied pressure vessels a long time ago, internal pressure inside of a pressure vessel causes both an axial stress as well as this other stress value that we call the hoop stress, right? So the axial stress would add for a member like this, if it had internal pressure inside of it, it would add along the y direction. If you had internal pressure, it would also add a hoop stress component that would add along the x direction. So then you could have multiple components of stress for a member like this. So that's a good question. But we don't have that here, so we're actually at this point done with patch number 1. Okay? Any other questions before we look at patch number 2? All right. Well, I'll tell you what. Let me slide all this stuff down a little bit. And I'll look at patch number 2 right underneath this member. Okay. Just like before, I'm going to draw patch number 2 such that it's oriented approximately how the patch number 2 is oriented in this picture. So I'll show it like this. Okay. All right, and then what? Let me put some axes on there as well, I guess. So Z goes this direction. and this is y. What components of stress act in patch number 2? Well, let me ask you this. Is there anything that holds over for patch number 2 from patch number 1 so that we don't have to do another calculation? Okay. I heard someone say torsion, right? That torsional stress exists uniformly around the entire perimeter of this round-shaped piece. So where I had that 305.3 KSI that I had down here, I have that again for patch number 2. What direction should that be shown? Okay. So think about this again. The direction of the 2,000 foot-pound torque on the front end of this would essentially try to twist this side this direction, while the other end was held this direction. Do you agree with that? Okay, yeah, the back stays still while the front end would maybe twist a little bit. Now the tricky thing about this, we have to show these elements with some amount of size or else we can't even draw them, okay? But whenever we draw them like this, the presumption is that they are so tiny, or that we can make them so tiny that essentially size isn't a thing, all right? But we draw them with some size, otherwise we couldn't draw them, right? But the idea is we could shrink them and shrink them and shrink them, and it wouldn't affect our conclusions, right? So it's important to have that in your mind kind of clearly, that these sort of represent these infinitesimally small elements of material. All right, so if that's the direction there, what direction should I show it on this patch? Okay. Same as I showed them just now. There would be a force, or a shearing force / stress that would exist this direction, and it would be held on the backside in this direction. And to make that a complete state of stress, I would show another stress here and another stress here. Okay, and this would be, again, this tau due to torsion, and it would have the same value that we just found, 305.3 KSI. All right. Well, that was easy enough. Now what? Okay. There will be another flexural stress for this one as well. What is causing the flexural stress for this element? Okay. Yeah, we have this 300 foot-pound applied moment on one end that is reacted at the other end. Okay. And, you know, the direction that's shown, it would have the effect for this rod, you know, I can kind of show it here, where it would start to flex back this direction, correct? I know that's kind of hard to draw, but it's back in that, the end of it would flex in the negative x direction, right? That represents a flexure around a neutral axis like this, right? The neutral axis that it flexes around is essentially the z-axis, and it creates stress in patch number 2, and the value of the bending moment that it has to carry is just going to be this 300 foot-pound that you see reacted at the wall. All right? So once we know that, we can calculate the flexure. Let me ask this. Is patch number 2, is it having to elongate or is it having to compress due to this stress? It elongates, right? So we show a stress that goes, you know, such that it lengthens, tries to elongate that member, and that's my flexural stress. Okay? And the value of that flexural stress is going to be equal to 300 foot-pounds. Okay, again, I don't really want those feet, so I'll put in a 12-inch per foot here. Then what? Okay, 1 inch over 2 to get the radius from the neutral axis, right? That's this neutral axis I just showed right here. Relative to, from that neutral axis to the to patch number 2. And then what do I put in the denominator? Okay, same thing as I had for the other one, basically. Pi over 64 times 1 inch to the 4th minus 1 inch minus 2 times 60 thousandths of an inch. All of that to the 4th. Okay. And what that gives me is 91.6 KSI. All right. Good so far. You all are making great progress. Are we done? All right. Rack your brain. Think if there's any other kind of stress that we have to consider here that that you've learned about somewhere along the way. Okay. I'll give you a little hint. What about this 500-pound force right here? And this 500-pound force up here? Okay. I hear some people talking about some shear. All right. And there was an effect that you learned about in one of your mechanics materials classes. We called it transverse shear. All right. In some cases, they might call it beam shear. Okay. And the idea of beam shear is the best way that I can think of to kind of describe this is if you take a phone book with like paper covers on the outside, it's actually pretty flexible if you flex it in the direction that the page is open. Right. It flexes pretty easily that direction. What if you try to take it and flex it along, like so that you try to flex the binding of it instead? That doesn't flex as well, right? And what's the difference? Because you actually have the same material that composes the entire thickness, but it flexes easily in one direction and it doesn't flex in the other direction. So there's got to be some difference there. And what's the difference? Okay. Yeah, intuitively, the thing that's the difference between those two directions is that in the direction where it's bound, it can transfer shearing stress between the layers of pages that compose the phone book, right? And that's the type of shear that we are trying to account for with the idea of transverse shear. Who here remembers the formula for transverse shear? Yeah, it has Q in it. Someone says, isn't that the one that has Q in it? Okay. Someone else says gross. All right. Okay. The formula for it was, you probably remember seeing something like this, VQ over IT. Anyone remember something like that? Okay. And most everything in this formula is not too offensive. Okay. What's V? V is just the shearing force. And so for our problem, shearing force would be what? 500 pounds. Okay. So that's not too offensive. Q. Everybody hates Q. All right. Q is not that bad. What is Q? Okay. Q is a first moment of area for just the area above a specific cut where we are evaluating this transverse shear. Okay? So let's, let's kind of figure that up just a little bit. In order for us to kind of know what we're talking about there, we need to know where we are planning on cutting the cross section so that we can evaluate the transverse shear. All right? And where that cut needs to be made is basically right where this, center line goes through right here. Okay? And the reason we're taking that as the location where we are cutting it is that essentially our worst case scenario for this, that phone book effect that I was just talking about, where the pages want to slide relative to each other as the phone book bends, right? Where that is worst is right at the center line, right, of this cross section. That's where the worst case transverse shear occurs, and it just so happens that coincides with patch number 2. This transverse shear effect gets less and less as you move outward away from this location, right? Right at the middle of the cross section is where it's the worst. All right? And so that's what we're needing to do. And we need to find the first moment of area of all of the area above that cut that I'm making right there. Okay? So let's draw what that cross section would look like. Okay? That cross section is going to be a half circle. Such that we know the outer radius and we know the inner radius. Okay? The area that we're talking about is this. Okay? And what we're trying to figure out is what is the first moment of area of that area that I've identified right there. Okay? Now here's a formula you might remember whenever we were figuring out this Q value, which is this first moment of area above the cut. You might remember seeing something where it was maybe a Z bar times A. Okay, and we have to define what those mean. A might be easy enough for us to guess. What do you think A is? Okay, that's just the area of, that we're cutting through there. So that's maybe easy enough. What is Z bar? Okay, yeah, it's the distance to the centroid of this area. Like how far is it from the axis where we made the cut up to the centroid of where that area is located. All right, now what we can do with this is we can essentially break this area into 2 pieces, right? We can have a solid half circle minus another solid half circle, right? So that's kind of the basic idea of what we want to do here. And let me do this instead of doing it with values in it just yet. There might be something valuable we can get out of this without having to put values in it. There might be something formulaic that comes out of it. And so let's do this without actual numbers just yet. Okay? Let me call this value RO and this value here RI. Okay? And let's just say here that Q is going to be equal to the location in the z direction of the centroid of the solid outer circle first, okay? And many of you may not remember the formula for how to get to the centroid of a half circle, and if you don't, that's okay. It is actually in the back of your textbook. Truth is, actually, I don't know if they have a half circle, but a half circle is exactly the same as a quarter circle, which is in the back of your textbook, okay? So and the formula for that is 4r over 3 pi. Once I say that, that probably sounds familiar to a lot of you. Okay, so 4r over 3 pi. So that's what I'm going to do here is 4 r sub o over 3 pi times what's the area of the solid half circle on the outside. Okay, area of a circle is pi r squared, but we don't have a full circle, we have a half circle. Okay, and so far what I've come up with here is a Q for a solid rod, right, where the outer radius of the solid rod is r sub o. What do I need to do to get this hollow shape? Okay, subtract something very similar, but what do? I put subscripts of my r's of I rather than o to indicate the inner radius. Okay, and this would be multiplied by pi r sub I squared over 2. All right, well, this is kind of cool. The pi's divide out. Okay, not only do the pi's divide out, we can combine our radius values and the rest of what we have here, the 4 over 3, 3 multiplied by 2, all that can be simplified to 2/3 of what? Okay. And so what I come up with here is a formula for the Q value through the center of a hollow, round rod. Okay? That's what this kind of formula thing comes up with here. Now that we have that, we can plug in some values, right? So the Q that we have for our particular case is 2/3 of, okay, RO is just 1/2 inch. And RI is what? Okay, it'll basically be 1/2 inch minus 60 thousandths, right? Rather than try to, I can do that. So 1/2 inch minus 0.06 inches, okay, that cubed. And once you punch all that stuff in, this gives us 0.026544. And what would the units be? All right. So now we have addressed the dreaded Q. Okay, let's go ahead and start building this up here. V was 500 pounds. Q is now 0.026544 cubic inches. Okay, how about I? We've already done this a few times, right? There's no difference now. Pi over 64 times 1 inch to the 4th minus 1 minus 2, 1 inch minus 2 times 60 thousandths, all of that to the 4th. All right, and now I have one other parameter that I need here. T. Okay. Anyone here remember what T was? Thickness, okay. Thickness of what? Okay. It's related to wall thickness. Someone says wall thickness. It's definitely related to wall thickness. Okay. It's a little bit trickier than that, though. Not much, just a little bit. What T refers to in this formula is the amount of thickness that you would have to cut through to make the cut that you just made. Right? How much material did you have to cut through in order to make this cut? Right? So it's not just one T. It is, we have a T here, right? Actually, I shouldn't say that. T, the T value that we're coming up with, is equal to the sum of those two thicknesses. right? So instead of just being 60 thousandths, it's 2 times 60 thousandths. Okay, so I'll put that up here. 2 times 0.06 inches. All right, and that should give us everything that we need for this transverse shear component that we're having to evaluate. Once I plug them in, it ends up giving me 5.62 KSI. Okay. So now another big question. What direction does that go? So now we know the value, 5.62 KSI. How do I evaluate what direction that shearing stress acts in this little element? Okay. Well, it actually winds up not being too difficult for us to figure out because we can use a similar thought process as we did for torsion or for flexure or any of these other ones. Look at the direction that the 500 is applied at point B, right? Where this, remember, this is point B. Back here, this was point A. Okay. And look at how that 500-pound force would affect the side of the element that it's closest to, right? Whereas the 500-pound that I had on the backside, pointing upward, would affect this backside of this element, right? Like that's the effect that those applied forces would have in terms of that stress. Okay? Does that help? And that's it, okay? So we basically add those shearing stresses on to our existing shearing stresses. Notice that they're in the opposite direction. And I'm drawing them in a different color here so you can tell the difference. Okay. This is that shearing stress due to the transverse shear. And that's just equal to that 5.62 KSI. All right, so we're actually almost there. I have one last little thing that I want, because you might remember what we're trying to find here is the stress components on the two patches. Okay, whenever you're reporting these, or if you're about to use them in a failure criteria, which is kind of the next phase of the class we're going to get into eventually, you're going to need to combine ones that act in the same direction, right, in the same general direction. So we only have one of those that we have to deal with here, and that is what? We need to combine the shearing stress that we had due to torsion with the shearing stress we had due to the transverse shear from flexure. Okay, and so what I would say here is that we can name it something like tau sub yz. Right? And tau sub yz is going to be equal what? Here's where we have to decide what direction is positive. Okay? And there's actually a standard for this to decide what direction is positive. So let me show you what the standard is. There's actually a standard for each pairs of direction, or each pair of directions, right? So I'll show you one of them right here. Okay, if you were dealing with XY, right, and we have an element that has a shear on it that is basically making an element do something like this, right? Okay, so a shear something like this. Okay, that is a positive shear. That one's not the one we need. What's the one we need? Okay. The one we need is the one where we have y and z. And if you have something like this in y and z, that is also a positive shear. And this is just a convention, in case you're wondering, right? This is just how everyone decided to start talking about positive or negative shear in these directions. The one that is a little bit trickier is, what if you're dealing with a patch that is in X and Z? Okay, this is one that, the one that if someone's going to be thrown off, it's usually this one that throws them off. All right, you have to put Z down here and X up here, and then look at a similarly shaped stress element. Okay, like this. Okay, and this would be positive shear in that direction. One of the ways that you can remember this is you can think of a cycle of directionality. So if we have X, X relates to Y, as Y relates to Z, as Z relates to X, for a right-handed coordinate system. Okay? That might be a lot to swallow right now. But this is, for now, you can just maybe remember this, right? That these are the positive directions for shear. You know, this is kind of our positive direction that we, or positive convention that we use here. So, now that I need to use this, what do I do? What do I take as my positive component for my shear that I was about to find? Okay, probably the piece that comes from torsion is the positive one, right? Because you might see there it acts, you know, the top acts to the right and the right acts upward in this YZ coordinate frame. That matches what I had down here, Y and Z. Okay, and so that would be the positive direction. So I would take positive 305.3 KSI, and then the negative component, the subtractive component, would be the one due to transverse shear. Okay, and so my tau sub YZ, trying to see if I calculated this anywhere. I don't know that I ever put that in. All right, let me calculate that real quick. So tau sub YZ just ends up being 305.3 minus 5.62. Okay, 299.68. KSI. That got all pretty messy right in there. Apologize for that. But that's our final answer for that tau component. Okay. We also have a sign convention for our normal component. Normal is easy to understand than shear, because the normal component is anything that's tensile is positive and anything that's compressive is negative, right? And so what do we have for this element? Tensile, right? So we can basically say here that the stress component that acts on piece number 2 is sigma y, and that's just equal to that 91.6 KSI, positive. Okay. Shall we do that for our first patch? We kind of skipped over it. We didn't think about all these issues with respect to the first patch. Okay. So maybe I'll do the normal one first. That one's easy. So the normal stress component would be what? It'd be in the y direction. Is it tensile or compressive? Tensile. Okay. Now what about my shearing component? Okay. Question is, does it match the direction I said was positive, or is it opposite? Okay, it is opposite of the direction I submitted to you that was positive, right? And so since it's the opposite of that, we would say here that this stress component would be negative 305.3 KSI. Okay. Any questions that you guys might have at this point? Yes.
One of these patches have been on the other side, so like, say number 2 was on the other side of it.
Okay.
The torsion would be the same, but would the other ones be different directions?
Right. So the question was, let's say we were looking at a patch on another side of the part. So let's kind of do a little mental experiment and see what we come up with. Let's say we're looking at the patch that's over, you know, where this comes around. There's another patch that mirrors the patch we looked at, patch 2, but there's another one that's kind of back there. All right? What would the stresses look like on that patch? Okay, maybe I'll draw that patch right here. Maybe I'll label it 3, right? This is patch 3. Okay, what direction would the forces act on that patch? Let's look at flexure first. Okay. If you have, right, if you have this end was stretching, then this end should be doing what? Compressing. Okay, so we would have in that y direction, where that's the z direction, right, we would have a compressive stress due to flexure, right? Would it have a different value than we had before? No, so this would be what? Okay, this gets a little bit tricky. Since I drew the arrows inward, I don't put a negative value, right? So relative to the direction I showed my arrows, I say that this is still a 91.6 KSI. Okay. Another standard a lot of people use for this is to always draw the arrows in a tensile direction, and then you use negative values to refer to a compressive stress, right? So, but you don't want to double up on that because then it becomes ambiguous, right? You could have a double negative there. All right. What about shearing? Okay. So for my torsional effect, the torsional effect, it essentially like kind of imagine it going all the way around and pushing that direction on the other side, right? Because it twists the same direction around the entire perimeter, right? So as far as torsion is concerned, over on this patch, torsion would do this. Okay, and it would still be 305.3 KSI. Okay, now what about my transverse shear component? Okay, relative to x, the YZ directions here, it stays the same, right? Because the 500-pound that pulls down right here would have the effect of still pulling down on that side of that patch, whereas the 500-pound I had on the other side would pull up, right? So my transverse component now goes the same direction. Okay. And it has the same value as it had before, 5.62 KSI. Okay. Does that make sense? So now we would have a more negative shearing component if you put them in the the YZ system there, right? They would essentially add, I guess maybe I'll go ahead and say them here, your tau sub YZ would just be equal to 305.3 plus 5.62, but that would all be negative, right? So negative 310.92. Yeah, so you're carrying more stress and shear on that side of it than on the other side of it. Okay. Now what about my normal component if I wanted to express it? Okay. In standard kind of formatting here, positive is tensile, negative is compressive. So I would say this one would be negative 91.6 KSI. Okay, and those would be my final answer for patch number 3 if I had to come up with that. Yeah.
What happens if you want to look at a patch that is out of your typical planes of your coordinate system?
So the next question that was just asked is, what if I wanted to look at any arbitrary patch located somewhere else around the perimeter? Like, you know, it's starting to get a little bit cluttered, but let's say there was a patch like right down here. I wanted to figure out what that one was, and it's not, you know, oriented relative to any of the planes exactly. Okay, so what do you think? Okay, have you all done like moment transformations and force transformations? Like you can put forces and moments into new coordinate systems? Okay. Like I could set up a coordinate system. Man, I'm running out of colors. Let me go to a whole new color here. I could set up a coordinate system such that it had an axis that went through this patch, and it also had a, you know, direction that was perpendicular to it. Well, each of the applied forces or moments that I have at location A, I could transform into being a combination of forces and moments in this new coordinate system, right? I could maybe call this x prime, and I could call this z prime. Okay? And if I can just transform a force that would have been in x and figure out what its contribution would be to x prime, right? And actually, once you've rotated it like this, it wouldn't just be forces in the x, right? Rotate it around the y, like I just did with this coordinate system. What you'd have to do is figure out a contribution of any forces that acted in the x and any forces that acted in the z. Those would both contribute to a component that would be now along the x prime. Okay. I'm actually going to do an example kind of like that later. All right. So I wasn't planning on getting into all that today, but we can certainly do that kind of a problem where we rotate our coordinate system to be able to accommodate any patch that was around the circumference of the member.